Hi everyone, so from this video onwards or in this video only we are going to start studying about hazards and we will try to cover PLDs as well, that is programmable logic devices. So we will try to cover both of the topics in this video itself. So first let's start about hazard. So what do you mean by hazard? So hazards are unwanted glitches in your output. Let's just say, let's look here. If I was expecting my output to be always 0, this is what I expected. But in the output you were having 0. In between there was 1 for a very minute time. Okay, I should not write it ideal, I should say expected, and this is the actual. Why this one is coming? Because of the delays in logic gate. So that we will see how this one will come. So because of that delay in logic gate, this one is coming. Or if you were expecting your output to be 1 always, okay, this was expected, but what you got? 1 in between there was 0 and then again 1. So this is known as static 1 hazard. That means 1 is static, in between there is 0. So static 1 is static and then there is a hazard. This is how you will remember it. Static 1 hazard means 1 is static but in between there is a 0. So that's why it is known as static 1 hazard. Here 0 is static, in between there is 1. So static 0 hazard. Okay, let's see the example, it will be more clear now. So this is a question you can say. So for t less than 0, a was 1, b was 1 and c was 1. For t greater than 0, a has become 1. So I mean a is 1 only, c is 1 only, but b has become 0. You need to draw the timing diagram of f. This we have already studied. Delays are mentioned 3 nanosecond, 2 nanosecond, 1 nanosecond. Without even seeing the final solution, you should draw it on your own. Without seeing the solution, draw it on your own. A, b, these values are there, these values are there, delays are mentioned, just draw it on your own. So this is your ABC diagram. Always 1, 1 to 0. What will be your A B bar? So A B bar for t less than 0. For t less than 0, your A B bar was 0. For t less than 0, your A B bar was 0. For t greater than 1, for t greater than 0, now input has got changed. So 1 into 1, A B bar I am calculating. 1 into 1, it would be 1, but it will take 3 nanosecond of time because the delay is 3 nanosecond. So here A B bar will say that, sir, I will be 1, but I need 3 nanosecond of time. So okay, you take the time of 3 nanosecond and then you become 1. There you go. 3 nanosecond of time it has taken. Just a second, I am having some headache. Just 1 second. Yeah, feeling fine now. So guys, I seriously need to maintain my sleep cycle. If you guys have some tips, then please do share it. Okay, in our WhatsApp channel, in our WhatsApp group, you can share how to maintain the sleep cycle. If you have some tips or tricks, I am not able to sleep properly. Okay, and that is causing me a lot of health issues. Yeah. So now B into C. 1 into 1, 1, and then it would be 1 into 0 will be 0. So 1 into 1, 1. Now it would be 0, but it will say that I need 2 nanosecond of time because the delay is 2 nanosecond. So it will be 0, but after 2 nanosecond of time. After 2 nanosecond of time. Okay. Now F. What F will do? Add both of them. It will add both of them. So adding both of them, 1 plus 0, that 1 plus 0 is 1. In between 0 plus 0 is 0. And then 1 plus 0 again is 1. Right? But this waveform will be shifted by 1 nanosecond. This waveform will be shifted by 1 nanosecond. So this complete waveform will be shifted by 1 nanosecond. So this waveform will start from 3 nanosecond to 4 nanosecond. So this we have already studied, right? These timing diagrams. That's why we solved it very quickly without even thinking of much explanation, because that we have already studied. So from 1 to 0 and then 1. What do you see? Which kind of hazard is that? Always you are expecting it to be 1. Why always you are expecting it to be 1? Because in this case what will be your output? 1 into 0, here you will be having 0, 1 into 1 is 1, 0 plus 1, 1. And in this case what will be your output? Forget about delay, I am directly asking the output. If delay is not mentioned, what will be the output? So 1 into 1, 1, and 1 into 0, here 0, 1 plus 0 is 1 only. So here also output should be 1. So you were always expecting, after making this combination circuit and applying these inputs, you were always expecting that my output will be 1. It started with 1, but in between for a minute time it became 0, and then again it became 1. So for this time it became 0. So here this is known as static 1 hazard. Basically 1 is static, but in between there is a hazard, static 1 hazard. Now solve this question. This was the first one. Here you got to know there is static 1 hazard. Solve this question. You need to draw the timing diagram. Inputs are same, just the delay has changed. This has become 4 nanosecond. So this waveform will be same as this. That sir, I will be from 0 to 1, but after the delay of 3 nanosecond. What the next guy will say? B into C. 1, yes sir, I will be sir 1 to 0, but I need the time of 4 nanosecond. Now tell me if I add them up. 0 plus 1, 1. 1 plus 1, 1. 1 plus 0, 1. Always it is 1. F is always 1. F is what? Always 1. F is always 1. Right? And this was 0, 1. Although there is some delay, but still there is no hazard. We will write down all the conclusion. We will see everything, but just now treat it as a question only. So it is always 1. Let's solve this question. Both delays are same. Both delays are same. You can make the timing diagram on your own. 0 to 1, 3 nanosecond, 1 to 0, 3 nanosecond. Right? 0 to 1, but I need 3 nanosecond. I will go from 1 to 0, but I need 3 nanosecond. Add both of them. 1 plus 0 is 1, 1 plus 0 is 1, always 1. So this is also hazard free. So only one case was there where there was hazard. Let's see next question. Now example has changed. These has become OR gate and this is your AND gate. And these delays are mentioned 3 nanosecond and 2 nanosecond. 1 nanosecond is there and you need to draw the timing diagram of F. So A plus B bar I need to draw. A plus B bar. A plus B bar. So initially it would be 0 plus 1, 1 and then it would be 0. A plus B bar, 0 plus 0 will be 0. So it will say I will go from 1 to 0 but I need 3 nanosecond of time. 1 to 0 but I need 3 nanosecond of time. Next is B plus C I need to draw. B plus C. So 0 plus 0, 1 plus 0 will be 1. So it will say that I will go from 0 to 1. 0 to 1. But I need 2 nanosecond of time. Now multiplication of both of them. So look, 1 into 0, 0, 1 into 0, 0, 1 into 1 is 1, 1 into 1 is 1, 0 into 1 is 0, 1 into 0 is 0, 0, 0, between 2 nanosecond to 3 nanosecond, between 2 nanosecond to 3 nanosecond, 1 into 1 is 1, and then 1 into 0 is 0, but there is a delay of 1 nanosecond, so it will be shifted by 1 nanosecond, so this waveform will be shifted by 1 nanosecond. So from 3 nanosecond to 4 nanosecond, from 3 nanosecond to 4 nanosecond. So 0 for a minute time it became 1 and then 0. Here you see what you were expecting, 0, 0, here you will get 0. In this case what will be your output? F. 0 plus 0 is 0, 0 into anything will be 0 only. And in this case what you would be expecting at F? B is 0, B is 1 here but C is 0, so this will be 0, so output will also be 0. So if you are not considering the delay, then you would expect that my output will always be 0, but there is some glitch, it is becoming 1 for a very minute time. So this is known as static, 0 is static, 0 is static, so static 0 hazard. Okay, now you can solve the same example with different delays as well. Here 3 nanosecond, you can take 4 nanosecond, or you can take both equal as well. In both of the examples, there will be no hazard. You can check it. What you need to do, you make it 4 nanosecond. Draw the timing diagram. You make it 3 nanosecond and draw the timing diagram. There will be no hazard. Now let's check a interesting thing. What was your f here? A plus b bar, b plus c. And what was your f in this case? A b bar plus bc, right? So in the previous case, what it was? A b bar plus bc. This was having static 1 hazard, right? In one of the cases, not in all cases, in this case, in the first case, it was having static 1 hazard. For the input of 1112 101, 1112 101, for the input of 1112 101. Okay. Now this is your A plus B bar into B plus C. This is having your static 0 hazard. In one of the cases, not in all cases, but there is one case that it is having static 0 hazard. For which of the inputs? 0002 010, 0002 010. What do you observe here? I'll look at it and think on your own. What do you observe? Dual, right? A b bar plus bc. If I want you to find the dual of this, what it would be? A plus b bar into b plus c. In dual, we do not complement the literals. I again and again say this thing. Do not complement the literals. So it's not that I will complement A. I will make it A bar plus B dot B bar plus C bar. No, no, no. Don't complement the literals, right? And one more thing we do. What do we do? 1 is replaced with 0. In when we take dual, I told you two things. Plus to dot, dot to plus, and 1 to 0 and 0 to 1. So 1 is replaced with 0. Here 1 is replaced with 0, 1 is replaced with 0, 1 is replaced with 0, 0, 1, 0. So if a circuit is suffering from static 1 hazard, its dual will suffer from static 0 hazard, with the condition that even the input should also be dual. 111 to 1112 to 101. Basically, I was changing my input from 111 to 101. So in the dual circuit, the input should change from 0002 to 010. Do you agree to this point or not? We can observe here. So this is the conclusion, right? So these kind of questions can come in 1 mark in true or false. Basically, they will state 4 statement and they will ask it true or false. So if a circuit is suffering from static 1 hazard, then its dual will also suffer from static 0 hazard, but with the condition that corresponding dual input combination should be there. F is equals to AB bar plus BC was suffering from static 1 hazard for this condition. Even if you take the inputs from here to here as well, no? Let's just say we solved this example where we were going from 111 to 101. If you were going from 101 to 111, that means for t less than 0 you are having 101, for t greater than 0 you would be having 111. Then also there will be hazard. Okay. If in one direction you are having hazard 111 to 101, then certainly in the opposite direction there will be hazard for sure. So in place of this, I should have made this arrow, that in both of the direction you can have hazard. So just take the dual of this. So F dual, that is A plus B bar into B plus C, will have static 0 hazard for 000 010. Okay. Now if there is SOP form, this was the SOP form, right? AB bar plus BC. So what you ended with? You ended with static 1 hazard. So if there is SOP form, then I will think about 1, static 1 hazard. And if there is POS form, then I will think about 0. So static 0 hazard. So in POS form there is a possibility of static 0 hazard. In SOP form there is a possibility of static 1 hazard. Okay. Now if some expression is given or if some circuit is drawn, so every time you cannot make a timing diagram to analyze whether there will be hazard or not. So what is the way? The way is to use the K-maps. Okay. So by using the K-map we can tell whether it is whether it will have static hazard or not. So let's take the same example which we analyzed, AB bar plus BC. So can I draw it in that K-map? Yes. AB bar, AB bar, BC, BC. So which two pairs I have taken? Which two pairs? Yes. Which two pairs I have taken? These two pairs I have taken, right? Is there any possibility to make another pair? Look, these two pairs I have taken, these are the best pairs, and this is my answer. But is there any other possibility to make another pair? Yes. This one. That means this box, this particular box, what it represents? 101. And what this particular box represent? 111. So if you are going from 101 to 111, then there is a possibility that hazard may occur. So how to eradicate this? So F modified. So which all things are already there? A B bar plus BC. So this is one of the other possibilities as well. So just include it, no? Just include it. So what is this? This is your A into C. That's it. So this will be hazard free. This circuit will be hazard free. That means if I implement this circuit, A B bar plus BC plus AC, then no matter whatever the delay is, TD1, TD2, TD3 and TD4, no matter whatever the delay is, it will never suffer from hazards. So what is the way? These kind of questions are asked, that what should be your modified F expression such that there is no hazard in all the delay cases. So what you will do, first you will implement this 1111, then you will see what are the other pairing possible, what are the other clubbing possible. This is the other clubbing possible, so I just need to include it here. That's it. Well and good. Okay. A plus B bar into B plus C. A plus B bar. A plus B bar. So this is what SOP form. Sorry, POS form. This is your POS form. So A plus B bar. A plus B bar into B plus C. So this is your A and B bar. B bar means 1. Right? This is your A, B bar. B bar, sorry. B bar. B plus C. B plus C. So this is the pair. This is the pair. Is there any other possibility? Yes, sir. This is the possibility. So what you need to do? What should be your F modified? A plus B bar into B plus C and then A plus 00, A plus C. This should be your F modified, right? A plus B bar into B plus C is also there, but this club I should also mention. Okay, so these kind of questions will be asked, that what you need to add more, A plus C. Okay, let's solve this question. BC bar, BC bar. So this is B, this is BC bar. AC, these two are A and this is C. AC. A bar, B bar, D. Which all pairs have been made? This pair have been made, this pair have been made, this pair have been made from their side. Now what else I can see? What I would see is that I will say that, sir, I can make this pair, sir, and sir, this pair I can make. This is what you will say, right? It is fine, it is fine. But what I would do is that this pair you can make and this pair you can make. But what I would do is that I will directly make this quad. It would include all, right? I will directly make this quad. What I was thinking, I was thinking to make this pair and this pair, which is other thing possible. But here I can see a pair of, here I can see a quad of 4 as well. So better make that only, no? Right? So this is one of the case. other what all things are possible? Others are possible is this can be one of the case. Other what all are things possible? This and this is already taken, this and this is already taken. From here nothing is possible, from here nothing is possible, from here I can see one more thing is possible, right? So these three pairs, 1, 2 and 3, 2 and 3, okay. So let's write down the expression now. So f is equals to whatever they have already taken, don't do anything with that. What about this? This is AB plus, what about this? This is CD and B bar, B bar CD. Basically this is complete CD and B bar plus A bar C bar D. This is C bar D and then A bar. So that's it. This is the expression. So from here only we have got our expression F. So very easy topic, very straightforward. How will you determine the hazards, and this is how you will make your design better. That means if I was having only this, then I could have hazard. There could be some hazards, but if I have made my design this complete, then it will be hazard free. What I need to do, I just need to see what all are the other possible pairs. So all possible pairs if I am writing, then irrespective of the delays there will be no hazards. Okay. So that's it about this video. That's it about the hazard. So I hope you must have understood it. One more small thing is there about the logic families. So this is the small information. So we have studied the classifications of all the logic families. So best fan in CMOS will have, best fan out CMOS will have, best least power dissipation CMOS will have, best noise margin means best noise margin means noise margin is high, best noise margin means high noise margin. This is also high noise margin. This is also high noise margin. And you would want your power dissipation to be low only, right? You would want your power dissipation to be low only. So this is having least power dissipation. But least propagation delay ECL logic gate will have. Or ECL logic gate will have. Least propagation delay ACL logic gate will have. So least propagation delay ECL will have. So in all of the things, best fan out, best fan in, that maximum input can be connected, maximum output can be connected, maximum noise it can tolerate, or least power dissipation, all of them CMOS will have. So this is something you can remember, and least power dissipation is ECL. Very rare chance that they will ask, but still you should remember it. Now I should continue now PLDs, but I am feeling something in my head. I don't know what is happening. It's like keep on revolving around. I know how I have taught all this. So it's just revolving around. So I need to take a break. But what I will do once I get fine, I will record the PLDs and I will add the PLDs in this video only. Okay, in this video only we will add the PLDs. So that we will study now. Fine. Yeah. So I will end this session. Then again I will record it and then I will add it up. Yeah. Hi guys. So I am back now. I am feeling much better. So let's start our new discussion, that is programmable logic devices. So a very easy topic, very straightforward. It is related to combinational circuit design, and in your interview it will not come. 100% guarantee they will not ask it. 0.01% chances are there that they can ask anything from PLDs. Okay, but in written test there can be some questions. In the gate examination there can be some questions from this particular topic. So that's why we are going to cover it for the purpose of written test and gate examination. Okay, very straightforward topic, you will be easily understanding it. Now if I ask you to implement AB plus BC, how will you implement it? That sir, AB, BC, and then sir there is a OR gate. So this is how you will implement it. Now this is how we were implementing all our combination circuit. Whatever the combination circuit we have studied, we were implementing in this manner only. So what is the issue with this manner? The issue is it is high cost, it is having high cost. Secondly, they will be difficult in testing. Why is that so? Because if I am saying that this node is A, this node is B, this node is B, this node is C, so I am fixing it. These nodes are fixed. So I am fixing these nodes, and these output nodes and which is being fed to the input of OR gate, these are also fixed. So they are fused there. Now if they are fixed, then it is difficult in testing. I cannot change it. They are not programmable, they are fixed. Here AND gate is also fixed and OR gate is also fixed. Nothing is programmable here. So that is the issue. That's why modification is difficult and it is difficult in testing as well. So implement the combinational circuit only, we use another way, that is programmable logic devices. So there are three kind of programmable logic devices, which are PROM, PAL and PLA. What do you mean by PROM? Programmable read only memory. So how would you remember it? PROM. So what do you see here? In between you see RO, which is equivalent to OR. So here OR gate is programmable. OR gate is programmable. What do you mean by programmable? That I will tell you. And fixed gate, AND gate is fixed. PLD will always be AND OR logic. AND OR logic. AND gate will be there and then there will be OR gate. So AND OR logic will be there. So if I am asking PROM, that means in between what do you see? OR. So OR gate is programmable, AND gate is fixed. If I ask PAL, so in between what is there? A is there. That means AND gate is programmable. What did I say in this one? AND gate I programmable, I said. No. OR gate is programmable. In between whatever that is there, OR gate is programmable, AND gate is fixed. Here what is in between? A is there. That means AND gate is programmable, OR gate is fixed. PLA. What is there in between? L. L stands for none. Neither it stands for AND, neither it stands for OR. That means both will be programmable. Are you getting this point? Here PROM. So OR gate is programmable, PAL, AND gate is programmable, L stands for none, that means both are programmable. If both are not programmable, that means that is simple logic circuit design, simple combination circuit design. So you cannot say that, sir, in PLA nothing matches, so that means both will not be programmable. No, both will be programmable. I am just telling you a way to remember, that someone will have a doubt, sir, that sir, in the examination I may think that, sir, L is there, so nothing is going on. That means both will not be programmable. No. What you are going to remember? You are going to remember that if I am studying PLDs, that means one gate has to be programmable. If nothing I am getting, that means both are programmable. Right? So this is the way you will remember it. So this is what I have written here. Full forms are different. A has nothing to do with AND. Here A has nothing to do with AND. OR has nothing to do with OR. This is just a way to remember. So programmable read-only memory, programmable array logic and programmable logic array. This is the full form. What is the scene here? Here AND gate is programmable, here OR gate is programmable, here both are programmable. Let's understand the meaning of programmable. Now let's start with PAL design. So these kind of questions will be there. Yeah, these kind of questions will be there. What you are doing? Programmable array logic, that means AND gate programmable. So questions will be there like in this manner, that sir, F1 is equals to A bar B C bar plus A B bar C. You need to implement this using PAL logic, programmable array logic. You need to implement it. So this is the order given, 3 into 2 into 1. What do they mean by that? The number of inputs are 3. The AND gate you are going to use is 2 and the OR gate you are going to use is 1. Number of output means basically OR gates. 3 inputs are there, 2 AND gate and 1 OR gate. So basically I am having 2 AND gate, 2 AND gate and 1 OR gate. Sorry, these are the 2 AND gate and 1 OR gate will be there. Now what they are saying, this is PAL. So what do you understand by that? AND gate is programmable. So there will be something different in AND gate. So what you are going to do, you are going to make a straight line and here also you are going to make a straight line. Right? Now what do you need? A bar, B, C bar. So this shows A bar, this shows B bar and this shows C bar. This is your C only, this is your B only, this is your A only. So you need A bar, B, C bar. So at the output what you are having? A bar, B, C bar. What do you need? A, B bar, C. So A, B bar, C. A, B bar, C. So at the output what you are having? A, B bar, C. So by the cross I am showing it. If I am putting cross here, that means A I am getting. If I am putting cross here, that means B bar I am getting. If I am putting cross here, that means these 3 inputs are there. To this AND gate, these 3 inputs are there. A, B bar into C. To this AND gate, these 3 inputs are there. A bar, B, C. No, I need A bar, B, C bar. So A bar, B, C bar. A bar, B, C bar. These 3 inputs are there. So this is how we represent it. Why we are representing in this manner? Because our AND gate is programmable, but our OR gate is fixed. Our OR gate is fixed because this is PAL logic. So OR gate is fixed. So these two outputs I am having. These two outputs I am having. Right? Now OR gate is fixed, so simple, the way I used to implement, the same way I will implement it. If OR gate is fixed, how do I implement it? In this manner only. So this is my F1 logic, which is I am taking A B bar C and A bar B C bar plus A B bar C. So in the examination, this circuit will be given and they will be asking you what is the logical expression of F1. Will you be able to tell? Yes, very easily. That's our A bar B C bar plus A B bar C. That's it. This is the AND gate. Very simple questions will be asked. Very straightforward topic it is. Now you need to implement A bar B C bar F1 and F2 using PL logic. Tell me what will be the order. How many inputs are there? 3 inputs are there. A B C, 3 inputs are there. How many AND gate you require? This will require one AND gate, one AND gate, one AND gate, and one AND gate. 4 AND gate you require. How many outputs are there, or you can say how many OR logic you will be requiring? How many OR gate you will be requiring? One addition and another addition. You will be requiring 2 OR gate. There you go. So AND gate are programmable. So 1 line, 2 line, 3 line and 4 line. So A bar B C bar, A bar B C bar. This is the output. Outputs also I need to show. A bar B C bar, and what I need? A B bar C. A B bar C. A B bar C. What else I need? A bar C bar, A bar C bar, and B C. B C. A bar C bar, B C, A B bar C, and A bar B C bar. Okay, now I just need to add them up. What I need to do? Okay, let me make the lines by my hand only. I will make a OR gate here, which will give me F1 function, and I will make another OR gate here, which will give me F2 function. There is one more thing. What is that? Look at the output logic. I am having these values, right? A bar B C bar, A B bar C, A bar C bar, B C. They can give the output in this manner as well. In what manner? In this manner. They will make a straight line. They will make another straight line. They will make a OR gate. They will make OR gate. And what I need? This I need. This I need. So they will just make a dot here, and in this one they will make a dot here. So if dot is there, that means it is not programmable. Not programmable. Dot is there, that means it is fused. This is fixed. And if a cross is there, that means you can change it. You can move the cross anywhere you want. But if dot is there, that means it is fixed. So this way, this particular design, this particular part can be represented in this manner as well. So in the examination, if they give you this particular design, they will ask you the expression of F1, F2, and they will ask you whether it is PAL, PLA or PROM. So don't think that sir, dot are there, so I would think that OR gate are also programmable. No. If crosses are there, crosses are being fed to AND gate, that means only AND gate is programmable. Dots are being fed to OR gate, so it is not programmable. So here only AND gate is programmable. So this could also be the way. Okay. This in some books you will find this is how the designs are made. So here you will not say that, sir, my OR gate is programmable. This would be my F1 and this is my F2. So OR gate is not programmable here. So this is also how it could be represented. Now let's see PROM. So in PROM, the interesting thing is the order is n cross m. What do you understand by n? So let's understand that by an example. You need to implement half adder using 4 cross 2 ROM. So what is the expression of half adder? A XOR B, or I can write some expression is this, right? And what is the carry expression? That is AB. So how many variables are there? 2 variables. 2 variables. And 2 variables represent total 4 combination. Or you can say total 4 minterms. So this is what this represent. 2 variables I have and I need to generate all 4 minterms, M0, M1, M2, M3. Which combinational circuit can generate it? 2 variables I am giving and you need to generate all 4 possible minterms. Which combinational circuit does that? Demux and decoder. So in PROM we will always use decoder. Let's just say if I apply 2 variables A and B, A and B, A and B, and I am asking them to generate 4 minterms, M0, M1, M2, M3. So will it be able to generate? Yes. Y0, Y1, Y2, Y3. E3 लिख रहा हूँ यार, बताओ. Y3. And these are the inputs X0, X1. So they will generate all the minterms, right? M0, M1, M2, M3, which is equals to A bar, B bar, A bar, B, A, B bar, and AB. Now the thing is, now you would say that, sir, you said that PROM, in PROM what will happen? OR gate is programmable and AND gate is fixed. So here I do not even need AND gate now. But in the decoder AND gate is there, no? This is your 2 cross 4 decoder. How would you make this decoder? How would you make Y0? You will put A bar here and B bar here. This will be your Y0. How would you make Y1? What you are going to do? You are going to put A bar here and B here. How will you make Y2? You are going to put A here and B bar here. This is how you are going to make Y0, Y1 and Y2 and Y3, right? So fixed OR gate is there. Sorry, fixed AND gate is there in the decoder itself. So in PROM, 100% chances are there that you would find this manner only. That you would find decoder will be made and minterms will be there, and from there you would connect your OR gate now. So in between the decoder only these AND gates are there. So you do not need to think that, sir, where are the AND gates? AND gates are there in the decoder itself. Okay. Now what do I need to do? I just need to use my OR gate. So A bar B, A B bar. This is the sum. And what about carry? This is carry. Carry is AB, which is programmable. So cross I am saying. So it is being fed with A bar B plus A B bar. Okay, this is the sum, which expression I am not gonna write. This could be the other way of representing it, right? From here A bar is coming and from here B is coming. So A bar B. From here what is coming? A is coming. From here B bar is coming. A B bar. From here A is coming and from here B is coming. So this is your AB. So if I cross on this, that means here AB is being fed. If I cross on this, that means A bar B and AB bar is fed here. This is your sum. So this was your decoder design only. Here we did not use A bar B bar. That we did not use because that was not useful for us. That was not even used. Here there was no cross. So when I was designing with AND gate, so what do you see here? These are fixed. These are fixed. But my OR gate is programmable. Again, I am having issue with my eyes. I went to the doctor today only. He gave me medicines as well. I don't know what has happened to eyes and head. Okay, let's see the next one. You need to implement 1456 using PROM. So what will be the order? What do you think? 1456. Three variables are there. 8 combinations. Wait a second. Yeah, so there are 8 combinations. So what would be the order? Order will be 8 cross 1. Why 1? Because one output will be there. You would need only one OR gate. So order will be 8 cross 1. How do you define this? There will be 3 variables, which could be anything. They did not give the name. So forget about, I will also not give the name. So, and 8 output combination will be there. Total 8 output combination is there. If I am calling this as M0, this is my M7. 0, 1, 2, 3, 4, 5, 6, 7. Yeah, what do I need? 0, 1, 2, 0, 1, 2, 3, 4, 5, 6 and 1 I need. आप सभी लिख देते हैं ना. Okay, so these I need. 1, 4, 5, 6. This is my F. Okay, so this is my 3:8 decoder. They can either ask the decoder size, or they can ask this total size they can ask, or they can ask how many AND gates you will use, how many OR gates you will use. These kind of questions they can ask, or directly they will make the design and they will ask what is your final output F. Okay, PLA, this is more interesting. So same kind of things are there: number of inputs, number of AND gate, number of OR gates, right? Or you can say number of outputs. So let's see this question. You need to realize full order. So here in PLA, what is the scene? Both programmable and or both programmable. So A bar, B bar, C. This is the sum, this is the carry. What do I need? I need 1, 2, 3, 4, 5, 6, 7. 7 AND gates I require. And how many summations are there? 1, 2, 3, 4, 5. Basically, I would require, sorry, there are 2 outputs only, no? There are 2 outputs only, this output and this output. So I would require only 2 OR gates. I would not see by the summation. I would see how much outputs I require, because this is programmable, or even if it was not programmable, still I can feed any number of inputs to the gate, right? Any number of inputs I could give to the gate. So there are 2 outputs, so I would require only 2 OR gates, and 7 AND gates I would require. So A bar, B bar, C, A bar, B, C bar. Okay, I will not say it because whenever I am saying it, this is vibrating, this head is vibrating. So I will just keep silence here. Okay, A, fine. AB, BC, CA, fine. So AB, BC, CA. Up last 3 are for AB, BC, CA. Last 3 are for carry. This is your CI actually. This is your CI. Last 3 are for carry. Initial 4 are for sum. 4 and 3. Sum and carry. Well and good. Okay. Let's see optimal PLA design. So from here questions will be framed. If they are asking questions from this particular topic, then from here only they will ask the question. Okay. You need to implement F1 and F2. Two outputs you are having, fine with that. How many inputs you will be having? By the min terms you can see there will be 3 inputs, 0, 1, 2, 4, 5, 6, 7. So there will be 3 inputs. How many AND gates you will be requiring? What do you think? 0, 1, 2, 4. So what it will be? Sir, it will be A bar, B bar, C bar, sir, plus A bar, B bar, C, plus A, B, C bar, plus A, B bar, C bar. What this would be? Right? So you would say that that's our 1 AND gate, 2 AND gate, 3, 4, 5, 6, 7, 8. But they have given only 4 AND gates. They have given only 4 AND gates. But you are saying that, sir, I would require 8 AND gates. So what you need to do? You need to reduce the expression and then you need to find if there is something in common or not. Here you can find that, sir, yeah, sir, this is common. So I wouldn't be requiring another AND gate for this. Basically, if I make A bar, B bar, C bar, so already I am having A bar, B bar, C bar. So this I can eradicate. Anything else you can find common? No. So you would say that, sir, at least I require 7. This would say that, sir, I require 7. But 7 is not the answer. You only can make 4 AND gates. So what do you need to do? You need to make some changes now. So how you will do the changes? You will draw the K map. But will you draw the K map for F1 and F2 only? No. I will draw the K map for K map for F1, F2, F1, F2 and F1 bar and F2 bar. If I find something common in between these two as well, let's just say if I find common between F1 and F2, this is also fine for me. F1 and F2 bar, because if I need to go from F2 bar to F2 bar to F2, that is very easy for me. What do I need to implement? I need to implement F1 and F2. Then I will find the common things, no? And let's just say if I find common between F1 and F2 bar. So from F2 bar to F2, I can go very easily. How I can go? This is how I can go it. I am having F2 bar. What I am going to connect? 1. What I will get? F2. And let's just say if I find something common between F2 and F1 bar. So I can also go it very easily. F1 bar, 1, F1. So from F1 bar to F1 very easy, F2 bar to F2 is very easy. So let's try finding the value. So this is the K map for F1, right? 0, 1, 2, 4. 0, 1, 2, 4. So what do I see here is that what will be the expression for this one? This is your F1 bar, right? This is your F1 bar. You can directly see this is your F1 bar. So what is this expression? Do I need to calculate it? No, I remember it. 3, 5, 6, 7. 0, 1, 2, 3, 4, 5, 6, 7. In the K map as well, you would be remembering this particular ones, right? What is this? Very important expression. AB plus BC plus CA. Like 100 of times I have told you that you need to remember this. 3, 5, 6, 7. And what is the speciality here? It is self dual, right? So what will be your F1 bar? A bar, B bar, B bar, C, C bar A. I am not only gonna even calculate here because I know this is a self dual function, so directly bar I can take. What about these now? This was actually F2, no? 0, 5, 6, 7, yeah. 0, 5, 6, 7, this was F2. So A bar, B bar, C bar plus A is there and then C plus A is there, then B, right? Directly I can see that I will make F1 bar and F2 because AC, AB, AC, AB. 2 these will require one this will require and one this will require 4. But let's make for F2 bar as well. This is your F2 bar. Let's make for F2 bar as well. 1 1 1 1. F2 bar A B bar C bar plus A bar C plus A bar B plus A bar B. You are not finding anything common between F2 bar F1 bar or F2 bar F1 bar. Wait a second, this was F1 bar, this is F1. Actually this is F1, no, this is F1, this is not F1 bar. AB plus BC plus CA is F1 bar, so the bar of that will be F1 only, no, so this is F1. So you are not finding anything between F2 bar and F1 bar, F2 bar and F1, or between F2 bar and F1 bar, or you are not finding anything between F2 and F1. Are you finding anything common? No. What you can see, this relation you can see, right? AC AB, AB AC. 2 this will require 3 4. 1 2, this is 1 2 3 4. So 4 AND gates I will require. So this is how I will make it. What do I need to make? AB BC, sorry, AB BC and CA, these all I need to make. So AB BC CA, and at last I need to make A bar B bar C bar. So A bar B bar and C bar. So this is having AB BC CA A bar B bar C bar. This is your PLA design. So this OR gate is also programmable. So what it is saying, that for F2 I need AC plus AB, AC plus AB plus this one. This is I need for F2, and for F1 what do I need? F1 bar actually. There here I will be getting F1 bar. So for F1 bar what do I need? AB plus BC plus CA. And what do I do is that after getting this, I make this one, I connect this as 1 and this one as F1 bar, and from here I will get F1. F1 bar XOR with 1. What that will be? F1 only. That's it. Now this question has been asked in your gate examination, that the minimum number of AND OR gate required for the implementation of this Boolean function using PLA. So how many AND OR gates will be required? So if you see it, you will say that, sir, how much will be required? Sir, this 3 6 7 3 6 7, these are common, so they will require 3 only, 4 5 and 6. So 6 AND gate and 2 OR gate, because 2 outputs are there, so 2 OR gate it will require, and 6 AND gate because 1 2 3 4 5, and in between 3 6 7s are common, so eradicate that, only 5 is new. So 6 AND gate, 2 OR gate, this is wrong. Always make the K map first. And they are implementing F1 F2 directly. They did not say that you can implement F2 bar, right? So you are not going to make F2 bar and F1 bar here, only F1 F2 you are going to make. Here as a designer I asked this question to you, that I have given it, then how will you do it? So there I can make F1 bar and F2 bar, but here they are directly asking that you need to implement F1 F2 directly. So I will not make F1 bar and F2 bar until they are specifying it. So I will make K-map for F1 F2. This is my F1. Right? This is the last question. After that, it will be completed. And I'm really sorry that I'm not at my 100% of the energy. But I guess I have given the required explanation. I hope you are comfortable with that. I hope you are not thinking that he is not giving perfect explanation, but I hope I have given the explanation perfectly, so that at least you should not be feeling like that we paid the money but what he is doing. Only in this video only I am at a bit less energy because I'm not feeling well, but as I promised I need to complete the syllabus by the deadline, so I will complete it anyhow. So that's why I am recording it. But this topic was very easy. If this was very extensive like HTA or FSM or delay based problem, then I would never be recording this video as of now, because there I need my 100% of energy. So but this was very straightforward. Even if I don't teach this, still you will be able to solve these kind of problems. So that's why I thought that I can make this video even if I am not at 100% of my health. So I hope you do not mind this thing. 3 5 6 7 0 1 2 3 4 5 6 7. So this I already know. What is this? AB plus BC plus CA. Zero, 1, 2, 3, 4, 5, 6, 7. So I can directly see 2 are being common here. First one, what do I get here? A bar, B bar plus this is BC plus this is AC. No, AB. This is A and B, AB. Okay, so AB, AB, BC, BC. 1, 2. This is also 1, 2. This would be third and this would be fourth. So 4 AND gate you require, and since 2 outputs are there, so 2 OR gate you would be requiring. Don't do like that, sir. 1, 2, 3, 4, 4 OR gate I will require. No, 2 outputs are there. So this will generate all these combination, and then 2 outputs will be there. So you can make cross cross cross, 1 output, cross cross, 2 output. Okay, so 4 AND gate and 2 OR gate. So these kind of simple questions are asked, and that's it about your syllabus. And if you are left with some time, you can do the CMOS VLSI part as well. I will add up the videos if you are left with some time. Otherwise, you can go to your next subject. Once you are done with analog electronics, then you can come back and do the CMOS VLSI part. Okay then, till then, thank you very much. I hope you enjoyed the course. Happy learning.